Okay, so lecture has begun. So you've turned in homework, have returned your previous homework assignment. We're going to briefly discuss, I posted the final project on Blackboard. And then today's lecture, we're going to be going over pipelining hazards, which recall from last lecture, I asked, like, what could be the problem with pipelining hazards. So we'll discuss those today. Data forwarding is a way we get around pipelining hazards, and exception handling is what happens when you have an instruction that does something you don't want it to do. Like, what happens if somehow the compiler puts in a opcode into the instruction memory that actually isn't in there. So first things first, let's briefly kind of talk about the final project. So the final project, you'll be combining all of the course objectives, so you'll have met everything after completing this assignment. Basically, you've done everything except putting the pieces together for a computer. You will now have all of these skills that you can put on a resume. And this is a project you worked in the project to design simulated the MIPS data path. So you have all the pieces. Basically, you're going to be going through, cleaning everything up, taking the feedback from my previous assignments. Some of you ran into those issues already when you're couldn't figure out why your PC relative and pseudo direct didn't work. Oh, because my adder still didn't quite work. So you fix your adder, get up to speed on that. So there are 3 parts of it. They have the due date. So part 1 is determining delays of the clock. That's due a week from today. A week from Thursday is convert the code in the project into project.txt. And then the last Friday of the semester before finals at 5 p.m. Is that, no, I guess no. It'll be on the next page. No later than 5 p.m. On Blackboard, I have it so that way it disappears at 5 p.m. exactly. So considering you have a month, I'm not really empathetic if you try turning it in at 5:15. So task part 1, you're going to be turning this portion in class. So the whole idea is you're going to be reviewing pages 8 through 14 to view the MIPS data path you'll be designing in order to design the delays. So I've given you an example of what I've done for the instruction memory. So element 1 is called instruction memory. Element 2 is the 8-bit header. I have PHDL files, and I have the delays, and I have these little calculations. You look here, orange 2 delays equal to red 3 plus red 4. Why is this necessary? So I'll show you the page 8 in a minute. Orange 1 delay is red 2 minus red 1 is 20 nanoseconds. It is necessary because the instruction memory results are produced 20 nanoseconds faster than the 8-bit adder, and you have to delay them so they all reach the instruction, the end of the stage at the same time. So if we go to page 8, I guess that's... all right, so here's page 8, sideways, but you actually have the instruction memory here, right? It's red 1 and red 2. And there's orange 1, just like I indicated. So you have to add a delay here. And that's done by figuring out what these delays are and then going through and seeing what I've done. So instruction memory, this is 120 nanoseconds, right? If you recall, this is 100 nanoseconds. So we have to add in a 20 nanosecond delay here. Right? So then I have all of this for, you guys can print these out. So the instruction decode. So the whole idea is you're going to be figuring out precisely how the delays are supposed to work. Execution stage. And you have all these pieces. You have a multiplexer, you have an arithmetic logic unit, you have an adder, you know how to do shift left 2. You have an AND gate, multiplexer. You have the data memory already done. You have the multiplexers. You just take the pieces you've done already and you figure these out. So the first one that's due on Tuesday is simple addition. You go through, you find red 11, you find out what your name is, you put the name of the VHD, what you called it in your previous assignment, and the delay, and then you go through red 16, orange 16 delay is equal to red 12. And you put that in there. Why do you do that? So this actually, now you can go through, and this will help you study for these MIPS data path type problems, because now you're going to be going through, why do I need this specific multiplexer? Why do I need to insert delay here? Why do I need to ensure that I'm not overrunning this? Once you get through this, and once you see the pattern, it's not going to be that terribly difficult. And then you add the clock length. The final clock you have in your test bench is equal to, I call this TIF, TID, T execution, T memory, and T write back. So orange 33 is equal to TMD. So here you're actually calculating the execution time of the data, of the time of the execution stage is red 11 plus red 18 plus red 15 plus red 14 plus red 16. Then you add those together, you add that together. So the whole idea is now I'm showing you, teaching you how to actually lay design out and how you want to lay the design out before you actually get to any code, right? So the second portion, which is due a week from Thursday, you have yourself some MIPS code. I want you to get the assembly code. Then I want you to do the RTL language, MIPS machine code, and put the machine code in the project.text format like we did in data memory. So we have these initialized values, and then I have a while function. So recall back from when we talked about all the way back in section 1 about MIPS and how it's a load store architecture. So did you notice that in the assignment I had to do load things into the instruction memory, right? Using program.text, and you got a datamem.text into data memory. And you notice how there wasn't one of those for registers? You're probably just grateful. You're probably like, you just didn't make us do it. This is where this comes back to haunt you, right? So if I have to get values into the registers and I don't have something I'm loading at the beginning of the instruction, how do I do that? How would I do that? You don't have anything in the registers. All the registers are initialized to 0, right? If you recall from coding it. But then I need to get these values somehow into the data path. How would I go about that? Yeah, they're not.
Is this data in text or at this point?
Right, yeah, everything's in data memory. So everything can be in the data memory where you have your data, and your instruction memory, we have the instructions. Today we'll learn about good reason to keep those separate. But
can we have the data memory write to a file and then?
Yes, and what type of instruction does that?
Write instruction.
No. Load word. I want you start first 0, instruction 0. You call whichever, you can pick your own register. So I want S0 is going to be I. So I do a load word 0. I can even give you a load word. I would say I is equal to S0. You've decided to do that. So the first instruction in there would be load S0, comma 0, and then you can call T0 your initial pointer to the array, right? So T0 would just contain the value 0. Or you could, what else could you do here? If you're pointing to the 0 instruction, right? 0 register, bingo. So if I wanted this next value, I wanted J, and I call J is S1. Wait, how would what would my next instruction be?
Load word S1 or T1.
Bingo. So now you swap. You would just load these into data memory. So you could say, you would choose a pointer to swap, right? And then you would say, in data memory, you would just have a value. So you would have 0, right? And then you would have 4 would be whatever you call S0, right? So I is 0, so this would be, right? 4 is going to be 3. Right? And then you can have the rest of these be your swap instructions, right? So you can have, let's call S2 as the base pointer to swap, right? So what's the value going to be in? So you have to load a value into S2, right? So how do you do that? You'll do load word. So now we're going to have 8 going to point to 12. And the reason why is because we're going to load the value of 8, so this is going to be 0, 0, 0, 0, 1, 0, right? 1, 1, 0, 0. So you know the load word S2, 8, 0, right? Does that make sense? And now you're going to load the value 12, which you're putting into your data memory, right? So now you put S2 into 12, and 12 is going to contain 1, 16, 20, and 24, right? 20 is going to contain what? If 16 is containing 1, because that's the first element of the array, what's 16 going to contain? 3. Bingo. What's 20 going to contain? 2. And what's 24 going to contain? 4. So that's how you build a data memory to do that. So then the next thing is you translate. So you have the 3 instructions, your first 3 load word instructions, and then you do this to calculate everything. Now, one other thing I want to point out, I'm going to erase this so that way you can. I have a pointer to I, right? Here. So I have some initial values, and then I call a function where I have a pointer to I. So what would I be doing here? How would I go about doing it? I know we say that we have the value of I is in S0 now, correct? But here's the thing, in a function, we're not passing by value, we're passing by reference. Since a lot of people have talked about struggling with code, let's actually deal with a coding example. I'm going to scroll up a little bit so people in the back can see. So I have this pointer star I. What does that mean physically? Yes, you do know. Come on, you do it. I know you do. I don't know. You guys have covered. You guys know what data memory is, right? How do we get information from data memory? We load how? We calculate with the ALU, right, to get a pointer. So you know what pointers are. That's what a pointer is. So if I have a pointer,
It's a reference to I.
mm-hmm. And where is, so the value's in S0, but where's the equivalent value in the data memory, which we just did? What's its location in the data memory file? Yeah, what was that address? 0, because that was the very first one. So what we're actually passing here, we're not passing S0 to the function, right? We're actually passing 0 here. So whenever we do this, what we're going to be doing is we're actually going to be doing load word, and we'll call it temporary register because inside the function, it's temporary. If you recall from coding class, stop me if you haven't heard this before. But when you have a function, you initiate a value inside the function. The moment you're done with the function, it's gone, right? Here's why. Because you have allocated a temporary register in the function, and the moment you jump out, back to main, or in this case, down to main, then the compiler says, I no longer need that variable. I can overwrite that variable. So that's why you've created a pointer, this load word T1, this 0T0 is the actual pointer, and T1 is the temporary value that you're going to be using. So here, we're incrementing I, right? So we have to increment I, so we add I, T1, T1, and 1, right? What else do we have to do? At the end of this while loop, before we leave the while loop, what do we have to do?
Jump back.
We have to jump back to the last after leaving the while loop. Before we leave the while loop, what do we have to do? Regarding our pointer. Yeah, you have to store it back into the data memory, correct? Because we passed by reference, we have a pointer, which means it's not a temporary copy. I'm pointing to it because I'm saying I want every update you make in that function to be reflected throughout the full program. So the last thing you need to do, you can have this J, you put the A into the VO, right? You add these up, but then you have to ensure that you do a store word operation. You do store word C1 0 ZER, right? That's the last thing you should do before you do the jump address. JR.
All right.
Yes.
Instead of doing S0, if instead of just using the 0 register there, if we had done just say put in a temporary register, would it just be that temporary register instead of 0?
What do you mean?
Right there, you've got 0 and then a 0 value. So if we put it in a temporary register, it would just be 0.
Well, that's what you're doing. You're putting it into a temporary register. But the thing is, with the data memory, you have 0 and then.
Oh, because it's a load. I'm sorry.
Yeah, it's a load word.
Okay, I see what you're saying. Yeah.
So if I was actually 1 in this case, it would be 1. And then what you're physically doing is you're going into the data memory, grabbing this copy, loading it into a temporary register, and then here we're turning it to 0, 0, 0, 0, 0, 0, 1, 0. So we have the temporary copies different, right? You see how that's different than this value? But it's a pointer. And what the pointer means is I want every change in the function. So now, every loop, you have potential change, right? So because of that, in order to do this, we have to take this value here in the temporary register, so the storage word, and we're putting it back here, which means we're taking this value here, and we're putting it back into the data memory, and so it becomes 1, 0. So that's how a pointer works. Do you guys understand now? I see a couple people shaking that. Yeah.
I'm sure I'm saying then that number will change as the numbers change from 1 to 3 to 4.
Yeah. You look skeptical.
Oh, no, I think I get it.
Okay. You think you get it? Andrew, you look skeptical as well?
Always
Skepticism keeps you alive. But does anybody actually have any questions about what I meant about how to handle this star I? When next Thursday, what I don't want you doing is I don't want you having this S0, right? There, correct? Does that make sense? If you're updating S0, or if you're changing if you're changing 0, right? You're changing its actual location, that's bad. Because if you're updating this value, this register here, first of all, you should never be updating the 0 register. But let's say we had a different register and we're using T0. If you're updating the value in this register, right? What you're doing is instead of changing the value, you're changing the location of the pointer. So now I'm pointing to something different. Like for example, let's say it was Thomas's birthday today, and we're supposed to give him a present. All right, but then I accidentally increment my pointer. Instead of giving the Francisco, he's like, wait a minute, it's not my birthday. I mean, I'll take it, sure. Like, I like free things. Now Thomas is mad because he has the wrong value. Francisco's now, he has extra stuff, which is bad if we're trying to control the entire data path, right? Because the whole idea, we're going to be talking about this today, is this concept of cache coherence. Well, actually, we won't be talking about this today, but we'll be talking about this in, especially in multiprocessing. The whole idea is you have to keep all the copies of your variables the same. And that can be quite the challenging problem. So the final one is putting all that together. So you'll have a data memory.txt, you'll have your layout, and you'll have 2 weeks to just put the pieces together. That makes sense? You know the buffer, you just hook them up exactly in the drawing, and I've given you directions on how to put the reports together. Now, you may not, like at this point, up to this point in the semester, you've been allowed to use online sources, right? As long as you cite. You may not use any online sources to find MIPS data path. Am I clear? Do not do it. If you do it, automatic F in the course. No chance. No second chance at this point. If you use an online source, and I know there's like 20 of them, and I know where they all are, and I know what they all look like. I would rather you turn in an okay final assignment that you did the work than try to get in a perfect score by turning in someone else's work. The whole point is, I want to see you do work. I want to see where you guys struggled. I want to see where you guys, overcame previous struggles in the semester, right? So if you turn in someone else's work, well, first of all, it's obviously not going to resemble your work from previous in the semester, right? Second of all, they have different things. They don't have timing constraints in almost all of the online submission. They don't have, they have different data path lengths. Some of them are 8, some of them are 16, some of them are 32. Some of them have floating point instructions in them. Some of them have, they're a little more comprehensive because they had more time, because that was all they were doing. So you'll have things in there that don't belong if you try to, so use common sense, don't do it.
It's like our whole funders online.
Mr. Skepticism suddenly is a lot less skeptical when it comes to someone else's work. You see what I'm saying? I want to see your effort. And remember I told you at the beginning of the semester, you're going to start developing this huge, set of code that once you apply for jobs, I'll have a thing that do you have any code samples, and you suddenly see like you have this big code sample. Once you do this final project, something you'll be able to do when you're applying for jobs, zip that, put it up there. Here's all this work I did in 385. Build a whole data path, and here's proof. And they'll look at that compared to somebody else who doesn't load up any code. That puts you ahead of somebody, right? So, because ultimately that's what you want to do. I mean, you can come here, I can think that you want to hear my wisdom all I want, but ultimately you want a job. So I'll try to put you in a position to get the best one possible. Does anybody have any questions on the final project before we go to pipeline hazards?
So we're going to be doing the delays,
Mm-hmm.
and then after the delays, we're going to be what was this step here?
You're actually going to be creating your own data memory and .text and instruction memory .text, right?
And we're going to map it all together and make sure that this can go through it.
Yeah. That's exactly what the compiler does. The compiler takes your instruction memory and data memory, and I'm standing in front of this, but all of my people who like just taking notes so they don't have to do homework later. The whole point is you're doing it just like the compiler. You're putting into the instruction memory, you're putting stuff in the data memory, and then you're letting it run. So that's the whole. Any other questions? Okay. So yeah.
I have one about the code you were showing. When you were showing this, all the equal to signs you would have used in branch on equal, like that while loop would have used.
What do you mean? Just that's there's a while loop, right?
Right.
So I want to do the code while the condition is met. Pay attention. Come on. You want to do all the code while the value in the instruction is being done, correct? Which means while it's met, you want to do the work. If that's the case, then you do the work. Otherwise, branch. The purpose of branch instructions is to not do the code that you don't want to do, correct? So all of the other equal signs are just equal signs. You're either putting it in the registers, or you're storing it to registers, or doing load and store operations. Any other questions? All right. So Let's now talk about pipeline hazards. So up to this point, we've tried to combine the data path into multiple stages, so that way we can shove all these instructions in at once. Ideally, we want to have it as K, where K is the number of stages, and MIPS that spot, right? Now, the problem is, you get these things called data hazards, structural hazards, and control hazards, which slow down, you have to account for them in your design. And if you don't account for them in design, it gets just vastly wrong data. So we define a pipeline hazard as a situation in which the next instruction cannot complete execution one clock cycle after the previous instruction. And this will become important as you work on these timing diagrams, what that means by you do the write back stage. And if you can't do the write back stage of the next instruction immediately for some reason, that becomes a pipeline hazard. So the first example of this is a data hazard. Instruction cannot be completed because the needed data generated by an instruction in the pipeline is not available. Now here's what that means. We have an instruction, we have an add here where we're adding 2 register values and then storing them in register 1, correct? Now here's the issue. I have 2 other operations, and I can't see this terribly well, but you'll be able to see this a lot better on the video. So on the write back stage, this is where I'm updating the registers, correct? Here. So if the next instruction requires register 1, that means I'm getting it from the registers and putting it to the ALU, right? But here's the problem. If I'm putting it out there, then I've updated register 1, but the value that is here, because these are by time. This is instruction over time graphs, right? It's all the same data path. So if I'm getting register 1 here, and I'm putting this value here, let's say register 1 was initially 4, and I've added to it, it's going to become 6. So at this time, from get add 4, I add 2, and the value circumventing data memory is 6, right? But at that exact same time, I'm at the next instruction where I'm getting register 1 from the registers, correct? It's still 4 here. So now I'm performing another ALU operation with 4, but I've updated to 6, correct? And I don't have the correct value. So we can't complete it because we would have to wait for the write back stage in order to have that registers right out there. Does that make sense?
Yeah. So this is the point where that experiment done with photonic whatever translations of something.
Right.
Would include an increase, so you wouldn't have to delay. You could just speed up incrementally in the registers.
Right.
Until the cycles were even.
Exactly right. At this level, before we get to like the photonic type splitting of clock cycles, at the silicon implementation like MIPS, we're going to be dealing with 2 ways called data forwarding and we're going to do skull insertion. So that's what we'll do with this if you're correct.
Can I ask one more thing about it?
Yeah, sure. What's up?
Would that be where graphene comes in?
Graphing?
Graphene at all?
Graphene, the issue with graphene at the moment is that while it's incredibly fast, the issue is that it's very difficult to tell the difference between a 0 and 1 using graphene implementation. So that's why you're not really seeing computers yet, because they're trying to do hybrid graphene silicon or hybrid graphene quantum or hybrid graphene other technologies to try to get that difference between the 0 and 1. Because ultimately you need to be able to use binary values. So graphene switches very fast, but that's because its switching is very small. So.
Also mass production is very expensive.
True. Very, very true. Does anybody have any questions about specifically related to data hazards? So before we go to structural hazards, does anybody think of remember these little dashes here are the buffers in between the stages? So does anybody think of any ideas as how we try to get around this type of data hazard? Yeah, we have it spliced up, right? So when do I physically have the value in the data path? Is it physically there? Yeah, when it's been calculated in the ALU, right? So you're talking about when I'm talking about when I say when is it physically there in the data path? It's physically there the moment it comes out of the ALU. So then it's sitting in this buffer waiting for the next clock cycle, right? So if I have the value there, and I have an old value in the registers that's going to be put out, how would I choose between those? It is a multiplexer, and so there's a type of term for it. So basically, I would forward it back here and use another multiplexer to choose between the value coming out of the register and the value coming out of the from the execution buffer, right? So that's exactly right. And there's a control, and you have to add another control unit to be able to do that. It's called a data forwarding unit. So we'll be learning about that later in lecture. But that is correct, multiplexer. So the next type of hazard is called a structural hazard. Two instructions cannot execute due to a resource conflict. So we have load word, subtraction, add, subtraction, and another load word instruction. So let's talk about a situation. Now we have the instruction memory and data memory separate in MIPS, right? So here's what would happen in this type of instruction if we just kept them together. Like we just had one giant memory, right? So we have sets of instructions and we have sets of variables separate in the memory. So when I'm doing this last load word instruction, this is at the data memory stage. So I'm simultaneously getting value from the load word and trying to get a new value from the load word, right? So if I had this store word instruction, so this is a better example store word here. Much better. It still works, but this is more clear to illustrate. So if it's a store word instruction, I'm simultaneously trying to write to the memory and read from perform the last operation. So the last load word, I'm trying to get something from the memory and write to it at the same time. Okay? So then you have an instance where you have memread and memwrite are both 1. So you don't want that because now I'm trying to read and write from it at the same time. And so that's called a resource conflict. And so what we would have to do is we have to insert a stall before the store word operation in order to ensure that this doesn't happen. And what I mean by a stall is it's called a no-op operation. And the whole idea is that you're not actually doing anything. All the control signals become 0. So you're not reading, you're not going to write to the registers, you're not going to read from data memory, you're not going to write to data memory, you're not going to do anything with notes in the ALU. It doesn't matter because reg write is 0, data write, mem write are all 0. So that's a no-op, right? And so you're going to have an instruction pause, right? In between. That's called a stall. Now the drawback of the stall is that, what? What do you think the drawback of the stall is?
Slows down the
Bingo. Reduction in performance. So this is where pipelining, you have to start doing these trade-offs. Okay, it runs a lot faster than single cycle, right? Well, we've already had to add a data forwarding unit. We're going to have a hazard detection unit so we can keep track of everything, right? We have to add more buffers. And sometimes we have to insert stalls to be able to, so the slowdown, the increase in performance has limits. Okay? And it requires a lot more hardware overhead. So. But if your customer desires a high performance, yeah, you're going to want to add pipelining to your data path. You just say it's going to cost you more. And if they're willing to go, sure, then you go ahead and do this. So the last type of hazard is called a control hazard. And the instruction to be fetched is not known. So in single cycle, we branch we've calculated our PC plus 4, right? And then we just PC plus 4 plus the branch address, and we go. Well, we don't calculate that until the third stage of the data path, right? So in between that, we have our instruction. We move to instruction decode, and we have another instruction behind it. And then this instruction is going to branch, but then we have another instruction that we might or may not want to do, correct? Right there. And so this is known as a control hazard because we have this branch equivalent, we have these 3 other instructions, and then we have this load word, right? So all of these instructions we might want to do, or we might not want to do them based on the branch, correct? So, but we don't know that until we get to the arithmetic logic unit. Does that make sense? We don't know that because we haven't calculated our 0 yet. So we don't know until real time whether or not we want to do these instructions or not. So we'd have to do something called a flush, which I'll show you an example of later. I want to flush these instructions out and then start with the new instruction that we get to. So define pipeline hazard, state, describe, and draw an example of each. That's TGO 6.18.
Now, the store ward one,
Mhm.
is that the, would
Yeah,
that
if you
be a
have-
problem
it-
because they're in 2 different parts of the.
Yeah, if you only had one, and that's the reason why they're split up,
Mhm.
is to get around structural hazards. You have to add a couple more control signals, but the purpose of that is to get rid of these types of hazards. Okay. Does anybody have any other questions about this? Does everybody see how this makes sense about how this is a control hazard? Because we're going to calculate it here, but we don't know whether these instructions are done yet. Yes. Okay. So, as you already predicted, data forwarding is using that multiplexer that George was talking about earlier into actually being able to forward a unit. Let me scroll up for those of you in the back. Data forwarding is the output of a resource used by an instruction is forwarded to the import of a resource being used by another instruction. So these types of resources can include the output of the ALU, the output of the data memory stage, and they would typically be forwarded back to the input of the arithmetic logic unit. Because the whole idea is, what we don't want is a situation where an incorrect value gets into the ALU. And then we do this by doing data forwarding. So we take this, we have these stages, we have fetch, decode, execute, memory, and write back. So I calculate something in my ALU, okay? And what I'm actually going to do is I'm going to circumvent the data memory and then get to the next buffer, right? So let's say we're using S0 as the output. That's what we're wedded to. And then we have an instruction, add S3, S0, and S1, right? So I've updated S0. So the value coming out of the registers is going to be incorrect. So what we're going to do is I'm going to have something called a data forwarding unit compare the value at these different stages, right? So let's add another. Add. Let's turn this to S0 as well as S4, S0, and S1. So now I have 2 changes on the instruction back to back. And this could be as simple as A equals B plus C plus A equals B plus C, and then the next instruction is A equals A plus D. That's a simple example right there, right? So I update the value, and then I'm going to update the value again in the next clock cycle, right? So we have a hazard if I have to wait until the write back stage to update the registers to then put it onto the execution stage, correct? That's the pipeline hazard. We'd have to stop it, so therefore we can't compute the instruction 1 cycle later. That's our hazard. So what we do is we have this data forwarding unit. It's going to compare the values on these buffers. And it's going to say, all right, I have on this third instruction here, it's going to say I have a value of S0 here. And I'm going to say I have another updated value of S0 here. And I'm going to say which one is the most recently updated. It's almost always going to be this, right? Actually, it's always going to be this. But you have to see if this instruction was like S4, when's my most recent copy of S0? If it's moved here after the data memory stage, it's no longer on the buffer, right? The value that's going to be on the buffer is the output of the ALU, which is going to be S2. So what's going to happen is I need to look after the data memory stage to see if I have another copy of that over here. If it is there, I'll forward it back, and then put in the ALU, use a multiplexer. So you're actually going to have 3 inputs to the multiplexer. You're going to have 0, 0, which is going to be your ALU input. You have 0, 1, which is going to come from your the execution data memory buffer, and you have 1, 0, which is going to come from the data memory write batch buffer. And I'll show you examples. We'll just go over examples of that in a minute. So we're going to be these pipelining stalls here, as I was talking about earlier, no-op cycles, where if you can't avoid it, and I'll show you an example. Our comprehensive example problem will be to show you an example where a stall is unavoidable. But this pipeline stall is when you actually physically use a no-op instruction to have a stall propagate through the data path where it's not doing anything. Control signals are all 0. Not going to write to the register, not going to read or write from data memory. It's all zeros. Definition: controller compiler inserts delays or no-op cycles between instructions in order to prevent pipeline stalls or prevent pipeline hazards. Pipeline hazards. Let me scroll past data forwarding here for a second. All right, so here's an example. So we have so we're going to show instances where data forwarding is required. So the initial instruction is sub 2, 1, and 3. So we're taking values from register 1 and register 3, adding them and putting them to register 2. Then we're going to be taking a value from register 2 and register 5, adding them and putting them to register 12. Or we're going to do OR on 6 and 2 and put the result in 13. We're going to put the result, add 2 here, add it to itself and put it in 14. And then we're going to take this value from 15 and store it into the offset of 2 and 100 here. So we're not going to calculate where we have to data forward, where our hazards might be, and where they aren't going to be. So the way to do that is to do these diagrams. So the first stage of the diagram is already up on the screen, but I'm going to draw it over here on the board to show you. So I have subtraction. We have 2, 1, and 3, right? So you have fetch, decode, execute, memory, and write that, right? So when is the value of register 2 physically available in the data path? After the execution stage, right? So it'll be here. So in this type of problem, we're going to talk about what happens if we don't insert stalls and don't do data forwarding. So the second instruction requires the value from register 2 and register 5 and adds it in 12, right? So I would require data forwarding to go to this execution, correct? Because I need it in the next instruction. And we're not updating 2, we're updating a copy of 12, right? So that means the most recent copy is not going to be after the execution stage, it's going to be after the data memory stage. Because if you recall from data memory, the value goes out the ALU around the data memory and to the memory to register multiplexer, correct? So value I have S2 is here initially. S2 is here. But now the value that's here, what's the value here being stored on the buffer? 12, correct, register 12. But here, what's the value stored on the buffer after the data memory? What value is stored there? So the result 12 from the current instruction. What's the value that we have stored on this buffer here after data memory? The previous instruction, which is 2. Bingo. So here's the thing. In the next instruction, I need a copy of 2, right? Because I haven't updated the registers. So what we're going to do is we're going to do data forwarding to the ALU. And so that's this one, right? So for those of you who are watching on the screen, can't tell what I'm talking about, I'll describe it again. So here, this blue, here is forwarding it from the output of the ALU to the input of the ALU on the next instruction. This register here, this blue value going here to the ALU, right? From data memory, I'm sorry, this one, data memory to the ALU. On the board, that's this one I've drawn here, right? Does that make sense? The whole idea is we're trying to get the most recent copy of the value before we write it to the registers, forwarded to the ALU so we can perform the operation with the correct result.
What is the little square in front of the register box?
That's the first register. There you go.
This one here?
Yeah, the little square in front of it.
Oh, 25 to 21, 2016. Yeah. Yeah. Right. So the next instruction requires 2 again, right? Now, if you notice, we haven't updated the instruction in 2 cycles, right? On this final stage, we're doing write and then read capability of the registers, correct? So we're writing to the register first, so we're writing S2 first, and then we're grabbing S2 from the registers to put into the ALU, correct? So you no longer need a stall. Here we're just updating the registers. That's what this little blue line from this register to this register means. And so that write and read capability in the registers ensures that we have one less pipeline type hazard. And that was specifically to avoid a data hazard because we only have the most recent copy, which means we don't have to add another instruction stall. And so if you notice, there are no more hazards. And the reason why is because now the value of 2 has the most recent copy. Once it has the most recent copy, you don't have to, you just get the value from the register and go. Does that make sense? And so, for those of you who guys see, I take shortcuts. I'm not expecting you to draw all these little things. You know, F stands for fetch, D stands for decode, E stands for execute, M stands for memory, W stands for write back. As long as you can use that to determine where your hazard occurs, that's fine. The reason they drew this out in the textbook is because they're trying to show you, and here's where the ALU is, there's a buffer on the pipe, forward. Here's where data memory is, we're circumventing it, right? And then in the registers, we're going to do write and read capability.
So, or?
Yeah.
Or the 2 was recently copied, right?
2, yeah, the 2 is being forwarded from that's this forwarding here. And the reason why that's this forwarding here is because I have the most recent copy is in the buffer between the data memory and write back stage. We haven't we have not written it to the registers. So we have to forward it to the input of the ALU. So that way we can perform the operation without having to insert a stall. And so here we're not, that's us, and we have 2 and 2, but here's the thing, the register has been updated using the write to read capability, so we can put both of those out and not have to worry about data forwarding because there's no more recent copy in the data path than what's in the registers. So therefore we can just go back to normal operation. Does anybody have any more questions on that? I believe the next one is the example. Yep, that's it. We'll probably end up spending the rest of the class doing that example. All right. Okay, so we have a code sequence here, right? So this is a very similar to something you'll see on maybe your final. So the whole, let's see, I want 5 volunteers. You'll each be a portion of the data path. I'll choose people. George, yeah, okay. My military people jump right up. What does Navy stand for? I mean, you're in the Army, but Navy tends to stand for never again volunteer yourself. Yeah. Yeah. All right, I need 3 more.
Oh, that's
All right. On Veterans Day, you're all making the military people do the work for you. Shame. 1 more. All right, there we go. I know that's the first time I've ever had to not pick somebody out of the class. That's good. So line up in a line. Actually, just move over a little bit because I want the rest of the class to see the instruction. You're going to be my instruction fetch, so I want you here. Instruction decode, execution, data memory, write back. Okay. So first instruction is load word. So what Andrew is going to do in the first stage of the pipe, right? Assuming no forwarding, we're just going to have, this is what's going on, right? So we're going to have to find our what this is called read after write dependency. So a read for something, I want to write to a register, but I need to be able to read from that register, correct? So that's, I'll probably reword that because I'm going to RAW this semester. Let's just call that hazards. There we go. That's a better way of phrasing the question. All right, so first things first. Andrew says, hey, I have a load word instruction. Hey, I have a load word instruction. And then buffer, right? Then the next clock, KB is going to output from the registers to the value. So he's going to hand them the register copies. And in that same cycle, you're going to say, hey, I got an add instruction. So you got, hold on, no clock until the clock happens, right? So what registers does Aaron, the ALU, currently have? Yeah, he's currently got the value coming from T5, right? And 40. So is a immediate value. So if you hand him, here is this one. So once you read data one, hold on, wait. I haven't done the next clock cycle. So you guys are just waiting. And so you guys kind of have it easy in this. So here, he performs the operation, and then he's going to now clock cycle, right? Aaron gives him the subtraction instruction. KB gives him what? T2 and T8, right? Correct? Give him T2 and T8. Aaron has given the results of T5 and 40 to George, and George is like, cool, now I'm doing a load operation, so what is George going to be doing? We are now getting the data from George. 40, and then what do you do in a load word operation? Write that, correct? So, sorry, on cycle? Clock, now what do you do? So you pick the easiest one. Alright, now it's that's fun. Right?
That's the first one.
Okay, no, sure. Alright, so now, we're now at you say, I'm giving you a store word instruction, give him a store word instruction. But before he did that, he has now he's given him the subtraction, so he's given him 2 and 5. But here's the thing. We've now loaded T2, he's thrown it back, right? Notice how he gave Aaron T2 before, right? And he gave him T2 again before Thomas threw back the value of T2, right? Before he did that, that means he was giving him wrong data. Because we didn't have a data forwarding unit, right? That makes sense? Except I got the wrong data in my hand.
Yeah, corrected data.
Yeah, you have corrupted data. We don't want to do that though, right? We need a data forwarding unit. Who's going to be my data forwarding unit?
Maybe be Josh. Well,
Yeah,
see.
I've messed with Josh enough today.
Don't make him volunteer somebody.
Thomas.
All right, you're not my data.
volunteered.
So we work with the compiler to make sure they don't make that same mistake, right? So that's part A, right? We now identify that T2 in these 2 instructions was a hazard because we didn't have the value thrown back. So the last thing is, in the subtraction instruction, so Aaron performed the operation to T3, gives it to George, right? In the clock cycle. But here's the thing. KB then gives him data from T3. Wait, my most recent copy of T3 is here, right? Now we have a data forwarding unit. This is where Thomas comes over and says, no! So you say, hey, and then what do? Yeah, he gives him, that's exactly what it is. Here you go. That's exactly what it is. Whoa, don't actually do that. Here, use this one. This one's much better, right? And then what's going to happen is then you're going to throw it back to KB. There you go. So now he's got that write and read capability. So we're getting around the T3 here. So if you're looking at this on the screen, I have the data hazards. The red from T2 goes to these two. T5 needs this value and this value. Now here's the last thing. I just described it, but this is a very common exam mistake. Common exam mistake, students miss this T3 here. Let me check this one here. So T3 is the result from the subtraction of T2 and T5, right? So now we're going to look and make sure we understand how the assembly language version of this. What? I changed that to store word. Okay. Store word. I've changed it because I in the past I realized that by not going over that it causes student confusion. So I'm making sure you guys have the best possible education. Okay, so T3, what a store word means is we're taking the physical value from T3, calculating the offset from 20 and T5, right? So what happens is Aaron calculates T3, gives it to George, right? So now what happens is KB says you're going to take the value from T3 and you're going to store it over there, right? To Thomas. So you're going to say, hey, give him, you're going to say that, here's your instruction. But here's the thing. The value that you want, that he had before, is not the updated value, correct? So here's what's going to happen. Tom's going to come back, and you're going to, no, I'm going to do it the other way around. So you're going to, yeah, bingo. Yeah. Now you can go to Thomas. Who, this is store word. Goes in his backpack, right? So that's how we get around all that, right? Does that make sense? Does anybody have any questions? If you have a question, this is your opportunity to make some of your classmates.
Data forwarding for every single cycle, just to make sure.
Yeah, data forwarding is checked every cycle. So what's going to happen? Then
So there are updated values, is that in the, okay, so the updated value stored, where is the, data forwarding?
The data forwarding unit is stored in
Hardware.
effectively hardware in in between the data memory stage. And we'll be going over the full pipeline data path later.
Okay. I mean, if it needs to be updated every cycle.
Well, it's checked every cycle. And then there's also multiplexers in between. This is a very good question. So Thomas is going to come back here. So here's what happens. I have potential data here from you, right? I have potential data from George, right? So what Thomas is doing, Mr. Gardner's doing, so it's Mr. Pitts, he's going to check Thomas data forwarding, Thomas write back. Thomas write back is kind of a cool thing. But what you're going to do is you're going to check these values here and see if those are the values that Aaron needs. So you're going to say, I need T3 and T2 to perform an add operation, correct? And what the data forwarding unit is to say, do you have T3 or T2? No. Do you have T3 or T2? Mm-hmm. Yes, I do have it. Okay, then the data forwarding is going to put this one back and go, that's the most recent copy. And it's done that by using multiplexer.
Oh, I get them from.
Yeah, you get it from
Okay,
I can just act it out. Well, show me master test scan. There you go. That's exactly how it's done.
Oh, because I'm not updated very well.
Yeah, because it doesn't get updated until you throw it back to the QB, right? So until that happens, I need this data forwarding unit to check you guys both, see who's got the most recent copy and give it back
And
to them.
then it's already checked for the data forwarding unit, it's already checked, and that cycle is checking again more times.
It checks it every cycle.
Okay,
It checks it every cycle. So if he sees,
so I threw it back.
if you have, let's say if you have T2, so if you have T1 and you have T4, and the instruction is S0 and S1, right? So you go to, do you have S0 or S1? You have S0 or S1? So you just go to that, just use the ones you had before that get the inclusion. That's how it's done.
If any of that information is like somewhere
Exactly.
between here, I need to get it. And then
And then give it to Aaron.
Exactly. Okay.
Make sense? Okay. Thank you, David Pat. Okay, so let's say we didn't have data forwarding in our data path, correct? What we have to do is we have to insert stalls into the values been updated. So the way to tell this when you're doing a problem is that you want to be, the way this is, assuming no forwarding, insert stalls as needed. So this portion is assuming no forwarding. Insert stalls as needed to overcome the hazards. How many clock cycles are needed to finish the instruction? So we have the normal instruction, and we're going to do write back, correct? So we have to do write back, and then to update the registers. So the trick that I used when I took this course was write back, and then I would have the first thing I would do before I write anything else is make sure the execution stage is in the next cycle. Because you're taking that from the registers and then sending it to the ALU. So what would happen is if I get rid of all of these, what I would do is I would say, well, 6 is going to be my execution because it needs to be after the write back, right? And so then I would go, well, instruction fetch, this is instruction decode, this is instruction fetch, but fetch would normally be happening here at cycle 2, right? So the way you do that is you have to insert one stall, you have to insert the second stall. So, next instruction. There we go. Everything should be right now.
So,
There we go.
so here it's just every time, if we don't have any forwarding, then we have to wait for the write back, and then we can do that.
There you go. So the difference between Part B and Part C is if we don't insert a data forwarding unit, which can be expensive, right? We're going back now. We're going back to we have a customer, right? Say, well, I can make this run even faster, but I need to hire Thomas to help out. If they have the money to be able to add that to the hardware. Sure, I can do that. If the improvement in performance isn't really that beneficial to me, I don't need Thomas. Sorry, get a job somewhere else, right? In this case, you don't require as much hardware. So, as a computer architect, as a computer engineer, maybe using the performance problems from back in section 3, section 1, right? In order to say, well, here's your performance with data forwarding, here's your performance without. And this is a good example. These part B and part C. So part B, I then have to have my memory and write back here. That was what was throwing me off. Does everything. Now I have yet another hazard because I have this T5 here, right? So I have to insert stalls to wait to update the value in the register and then be able to use T5 to add T2 to then put into the subtraction instruction, correct? So that's where we insert these stalls. Execution stage right after the fetch, because I want to get I have to write back because I want to write then read this WD here, this W and this D, for those of you watching later on the video, W and then D here. That means write then read capability of the register. So I'm writing to the registers and reading from the registers, putting it onto the buffer in between, and then executing in the next cycle. And last but certainly not least, that's T5. Let's just make that black so it's easier to read. Again, we have our hazard is here, as we've indicated before, this T3 here. We have to wait for T3 to update on the subtraction, and then we're going to store the value from T3 and put it into 20. And so again, we wait for the write back. Okay. So once we finish that, I'll dismiss you guys. And then store it into T5. So we have to insert 2 stalls again. So the cycle becomes 14, right? And then for part C, this will be the last part of the problem. And then before I do that, the homework is TGOs, what? 18 through 20. Okay, so let's do this last part C here, and then I'll dismiss you. Okay, so here's how this works. Load word, we're taking a value from 40 in T5, and we're putting into T2, correct? So when does the value of T2 physically become available in the data path? After the execution stage? It's a load word instruction. When does the value of T2 become available? After data memory, correct? And the reason why it's after data memory is we use the value from the ALU, getting the T5 from the registers, plus the 40, which comes from the offset in the I-type instruction. They're added together to create the pointer to data memory. Next cycle, data memory gets the value that we have from George and puts it out, and we have a buffer in between Mr. Humphrey and Mr. Pitts, right? And so after memory, that's when it's physically available. Once it becomes physically available, then Mr. Garner would take it back to the ALU, like this, correct? So that's why execution is after memory here. But if you do it backwards, you look, and there's a case where the skull is unavoidable there, right? But here's the thing. When's the value of the next value of T5 going to be available here? Right after the execution, so I can just export it back to the execution stage. No stall needed. When's T3 going to be available? Right after the execution stage. So I just do execution stage again. So the improvement in performance with a data forwarding unit over a data forwarding 9 unit is 14 divided by 9 in this case.
Choosing between stall and forwarding, just kind of a classic cost performance.
Bingo, cost performance. That's for the 4 design principles. That's the battle between make make the common case fast versus good design requires good compromise.
Is there any other reason to install the subboard besides just the hardware?
No, that's pretty much it. You would want high performance in most cases. Okay, so if anybody does anybody have any other questions?
Sure. Hey, real quick.
Sure.
So this one says, identify all pipeline hazards between pairs of instructions.
Yeah, so the red here, okay, this is a good question. So if you're looking back on the video, I put where the hazards exist as in colors. So T3 is a T3 hazard in blue. T5 has these two hazards here in green, and the red here, T2 and T2. So those are where the hazards, the different hazards exist. Does that make sense? Okay, there's no other questions. You are dismissed.